In this video, I'm going to talk about AHU selection and the important considerations during the selection process. As we know, inside an AHU, there are two critical components. One of the component is the cooling coil, and the second component is the supply air fan. So both of these components, we will have to size it. But of course, most of the manufacturer will have a combination of cooling coil and AHU fan. So the cooling coil will determine what is the cooling capacity of this particular AHU, whereas for the fan, it will determine how much airflow rate this AHU can provide. So for the airflow rate and cooling capacity, usually it depends on how much heat is needed to be removed from a particular space. So this process is usually done by using some specialized software such as E20 or HAP. Over here are some of the essential parameters for AHU selection. So just now we mentioned about cooling capacity, but cooling capacity actually made out of two parts. First is the total capacity that this particular AHU is able to provide, the total amount of cooling it can provide. And secondly, usually in the catalog, you will also see how much sensible heat this particular AHU can remove. Because for certain space, if the latent load is very high, then in terms of the cooling coil, you may have to upsize your cooling coil, because at a certain size certain phase area of cooling coil, it can only remove certain amount of sensible heat and total amount of heat. Secondly is the temperature. So what is the expected mixed air temperature that will go inside the AHU is also critical. If this AHU is serving, for example, a hospital, and all the air is actually from outside air, and there will be no recycling of return air, then your sizing will be a bit different from a typical operation where the fresh air may only be 10% or 20%. So other than the mixed air temperature, and what are the expected supply air temperature that you want this AHU to provide, it is also quite critical. As for airflow rate, it depends on what is the total airflow rate that this particular AHU is able to provide when all the VAV box is open, all the VAV boxes are at 100%, whether this particular AHU are able to provide a total flow rate. And of course, during operation, let's say all the VAV boxes are 70 or 80%, whether it can meet. So usually if it can meet the total airflow rate, then is able to supply, then this particular fan will be suitable. Then lastly is the static pressure. Static pressure, there are two aspects. One is external, the other one is internal. So let's talk about internal static pressure. Internal static pressure refers to the AHU when it is flowing across the cooling coil, when it is passing through the filter. There will be some pressure loss. So what are the total pressure losses when the air come back from the return air side and go out from the supply air side? So this is what we call internal static pressure losses within the AHU. And as you can guess, for external is after the air go out from the AHU, it will passes through some elbows, some junctions, and maybe pass through some dampers, then finally at the diffuser. So all these will contribute to the pressure losses along the way. So you will have to find out what is the total pressure losses that the AHU fan need to overcome. So over here are the important parameters within the AHU selection. So if the cooling capacity is high, then obviously the cooling coil phase area need to increase. And also the number of rows of tubes, which means the cooling coil tubes will also be a factor. So usually it's in multiple of 2, either 2 rows, 4 rows, 6 rows, or 8 rows. So in this diagram, as you can see, there are 4 rows. 1, 2, 3, 4 rows. So if you have 6 rows, then there will be another 2 tubes that will carry chilled water going in and coming out. So if you increase the number of tubes, then it is capable to remove more heat as well as lower down the temperature. As for the fan and motor, if you increase the fan and motor, will be the one that determine the airflow rate and static pressure. So if you need a higher airflow rate or you need to overcome more static pressure, then you will have to upsize the AHU fan. So this is the cooling coil side, this is the AHU fan side. And finally, the dimension also is quite critical, because usually AHU are inside a room, for example an AHU room. So whether what is the area that you need to cater for your AHU, do you have 2 AHU or 3 AHU inside the room, then you have to cater for that. So this catalog from Johnson Control, York, and there are some observations that we can make over here. So as you can see, if this is the airflow rate that this particular model is able to provide, and that it comes in 2 different types of configuration. One is 4 rows, one is 6 rows of cooling coil. And the inlet water temperature, so it depends. If the inlet water temperature is 7, then of course the amount of heat that it can remove will be slightly lesser compared to when the inlet water temperature is 5. Alright, then the sensible heat, as I mentioned just now, there's sensible heat and total heat. So if it's able to satisfy the total heat but unable to satisfy the amount of sensible heat, then you will have to maybe upsize the particular model. As for the chilled water flow rate, when you see when the total heat reduces, the flow rate will reduce as well, because this is what we have learned previously. Q is equal to mc delta T. So when the heat load reduces, the flow rate you can also reduce it. As for the water pressure drop, it will also reduce if the load when the water flow decreases, because it flows slower now. Alright, so observation from these 26 degrees Celsius, 20 degrees Celsius wet bulb to 27 and 19.5, you can expect that actually the sensible load increases from 26 to 27. Alright, that means the mixed air that come into the AHU has a higher temperature now. Let's say 27 degrees Celsius. But the wet bulb reduces. When wet bulb reduces, the humidity actually drops. So we can guess for this particular column, the sensible load is lower, but the latent load is higher, as we can judge from the dry bulb and wet bulb temperature. So let's take a look, maybe at 9 degrees Celsius. The total heat load is 6.8, sensible heat is 4.8. As for the column of 27 degrees Celsius, the sensible heat increases. So as you can see, QS is actually higher at this particular column, but the total load drops 6.5. And if you take the delta, you take the difference between these two, is actually the latent load. So this is what I mean when the air that is coming in has a higher sensible heat, then it will fulfill certain condition, and you will have to do the you will have to make sure that you choose the correct model, all right, and correct size for that particular air condition. Okay, now of course, definitely for full fresh air, the load will be the highest. Okay, so one of the important part of AHU selection is of course to size the AHU fan. Alright, so cooling coil depends much on the cooling capacity, how much heat you need to remove, and the AHU fan will take care of the airflow rate as well as the amount of pressure that it needs to overcome when it moves from AHU all the way to the very last diffuser. So these are the components that will contribute to external static pressure losses. So we have the fire damper, fire and smoke damper. This damper will be installed at the supply air duct. And what happens is, let's say when there's a smoke, when the smoke detector picked up that inside the duct there's smoke, the damper will start to close to prevent the smoke from spreading to the other rooms. So that is the use of smoke dampers. But 99.9% of the time, these smoke dampers should always be open. It is never closed unless there's a smoke in the room. Alright, then sealing diffuser. The purpose of diffuser, of course, is to spread out the air when it comes out from the diffuser, such that the airflow is more, the temperature will be more evenly distributed. Alright, then we have the volume control damper, which is also commonly known as variable air volume, and sometimes it's inside a box. We call it VAV box. Okay, air filter. Alright, air filter is more of internal static pressure loss. So these two are more of internal. Alright, so these two are more of internal static pressure losses. External are those that is outside the AHU and along the duct. Okay, of course, last thing is the duct fittings. When you need to transport your air and you need to move in a certain direction, for example, towards the left or towards the right, then you will need to use a duct fittings. To calculate static pressure loss, there is a formula. So the formula is this: pressure loss is equal to half K rho V square. So what are all these terms? K is the loss coefficient, and it depends on the types of fittings. For example, a simple example is, let's say you have a 90-degree elbow compared to a 45-degree elbow. So these two will have a different K value. So this particular K value will be higher. K1, for example, this is K2. K1 will be higher than K2 because for a 90-degree turn, there will be more losses. You will incur more losses compared to a 45-degree bend. So the higher is your K value, the higher will be the pressure loss, and the relationship is linear. Okay. And next, rho. Rho is actually air density. Air density usually around 1.2 meter cube per kg. At around 20 degrees Celsius is around this value. And for V is velocity of the air when it passes through, let's say, a fitting, or when it passes through a junction. What is the speed that it is traveling at? And for V, right, the relationship is not linear, is in a square relationship, y equal to x square kind of relationship. So as you can see, velocity actually impacts the pressure loss much more compared to K value. So the airspeed, the recommended airspeed, usually when it just come out from the AHU, it should have an airspeed of around 6 to 8 meter per second. But I have to mention that when it passes through the cooling coil, okay, when the air passes through the cooling coil, the airspeed is usually around 2.5 meter per second. And usually we will design based on this value. So this is what we call phase velocity, which is the velocity when it passes through the cooling coil. Alright, and why is that? So why they want to limit it to 2.5 and not 6 or 8 or 10 meter per second? Because if the airflow is too high, and as we know, in the cooling coil there's condensation. There's condensation formed on the surface of the cooling coil. And if the airflow velocity is too fast, if it's very fast, then it will carry the moisture with it, and it will maybe spread to the rest of the components. It may damage your sensors or whatever that you install up front. Alright, or it may also go inside your fan, alright, which is in front of the cooling coil. So usually the phase velocity is around 2.5 meter per second or 3 meter per second. Alright, but when it comes out from the AHU, based on the duct size, it will have a certain airflow rate. Alright, so this is the supply air duct. Okay, so let's say the duct size, the main air ducts, okay, you will have to size it such that the airspeed is around 6 to 8 meter per second. And when it travel downstream, the duct will get smaller and smaller, then the airspeed will also reduce along the way. So the main branch is 6 to 8 meter per second. The side branch is around 4 to 5 meter per second. Air distribution duct means the flexible air duct. So you have a side branch over here, then maybe it passes through a VAV box, and then maybe flexible tube, alright, flexible air duct before it go into a diffuser. So the flexible duct velocity will be around 1.5 to 2, and finally when it comes out from the diffuser, it should be around 1 to 3 meter per second. It shouldn't be too high. If it's too high, then the noise level will be quite high, because this is where the where all the occupants are, and it may affect them. And the airflow rate when it's too high is also uncomfortable. So to calculate the losses for fire dampers, all the duct components, other than using half K rho V square, okay, half K rho V square, which is what we use to determine the pressure loss, maybe at duct fittings. For components such as dampers, usually the manufacturer will have a chart like this. Alright, so the chart will need the air velocity value and maybe the different types lah. So if let's say you know what is the air velocity value when it passes through that particular duct, let's say 8 meter per second, then, and let's say you are installing a type C fire damper, then you can read off what is the pressure loss when it flow through it. So this is a value that you will consider as well when you total up the external static pressure. As for VAV damper, there will also be another chart. Okay, there will be another chart. So VAV damper also largely depends on the velocity when it passes through the VAV box, as well as what is the normal opening. Alright, because VAV box, it can open from 0% to 100%, but in operation usually is around 50 to 100%. Alright, so let's say you have a box, this VAV is usually at 75% open and is traveling at maybe 6 meter per second. That's where you can get what is the pressure loss by looking at the left, okay, the vertical axis. As for flexible duct, you can see that the chart is slightly more complicated, because when the flexible duct is straight compared to when it is very curvy and very bent, the pressure losses will of course be different. So once you know the velocity and the particular round duct diameter, you will have two types of pressure loss. Okay, one pressure loss is when it's straight, and the other one is when it's kind of like a worst case scenario. Alright, so it will be in between these two particular pressure drop. And for air diffuser, which is the very last part, there will be also some pressure losses. Alright, so if as for diffuser, we are not so concerned about the air velocity. Usually we size the diffuser based on the airflow rate. So for example, we know that 55 liter per second of air will pass through this particular diffuser, and from there you will be able to find out what is the velocity. Okay, the symbol is over here. You can find what is the velocity that comes out. Alright, the throw means, let's say you have a diffuser. Alright, let's say you have a diffuser over here. The throw means what is this X value, how far can it throw. Alright, throw the air to. Alright, so this is the X value. Total pressure, alright, that means the amount of pressure losses, which you can retrieve from here. Okay, the third value. And noise level is in dB. Alright, of course the effective area that it can cover. Okay, effective area is over here. Alright, so noise level, as you can see, let's say we are going to we have this amount of air that needs to come out from this particular diffuser. You can choose a 160 mm diameter diffuser, but it will be slightly noisier. Alright, it will be noisier over here. Okay, but if you want it to be not as noisy, alright, to be less noisy, then you may have to select a bigger size one, maybe 315 mm. Then when you select a bigger size diffuser, the noise level will drop, okay, as well as the pressure losses will also reduce. As you can see, the pressure loss now reduced to 1.2 Pascal. Okay, but the problem is the throw will be lesser because the speed when it come out, right, if it's not as fast, then the throw will be lesser. Alright, it will cover a smaller area. Okay, so the bigger is the diffuser doesn't mean it can cover a bigger area. In fact, it's the opposite. The bigger the diffuser, the smaller is the coverage. The one that will affect how far I can throw by right is the amount of airflow quantity. Alright, the amount of airflow quantity. If the airflow quantity is already fixed, the bigger is your diffuser, actually the smaller is your coverage.